Hey everyone, in a previous video we solved problem 1 from LeetCode in APL and we used an outer product to generate all the possible solutions and then we checked for the ones that we cared about. And in this video we're going to solve problem 1 again, but we're going to take into account the follow-up question. So the follow-up says or asks, can you come up with an algorithm that is less than O(n) squared in time complexity? And the answer is yes, we can. And so I described it briefly in the previous video, but I think I'll do that again here. So let's see, can I? Yes, I can. Where's the... So these are just some numbers. And now my target in here was 9, correct? Yeah. And so the idea is simple. The idea is that we have a list of numbers that we assume is sorted, and then we create two pointers, one on the left and one on the right. And then we see, well, what's the sum of these two numbers? What's the sum of the first and the last elements of the array? And in this case it's 17. But wait, 17 is too big, right? We want 9, and 17 is too big. So what we do is we get rid of the last element so that we make the sum smaller. Now, the sum of the two ends of the array is 13, but wait, 13 is still too large, so we remove the last one, and now 2 plus 7 is 9, so we found our solution. Now, if we had a, let's see, can I make this, let's make this a 1, and let's say that the target is 18. So this is what we have now. We have these numbers and the target is 18. So we start again with the arrows here, but now 1 plus 15 is 16, which is not enough, and so we need to get rid of the smallest element in order to increase the sum. But now 2 plus 15, well, this is 17, still too small, so we get rid of... Oh, this shows a problem. Oh wait, it doesn't, sorry. Yeah, everything is fine. So 2 plus 15 is 17, so we get rid of the 2. Now, 7 plus 15, this is 22, which is too large, so we get rid of the last one. And yet again, 7 plus 11, oh, okay, so this is 18, so we get the 7 and the 11. Now, obviously, this also works if we have numbers in the middle, so say there's a 9 there. No, we can ignore this, sorry, so let's delete this. So there's a 9 in here, right? So when we write out the numbers and we go through this process, we get rid of the 1 and then get rid of the 2 and then get rid of the 15. And what we see is that the first and the last elements add up to what we care about. So it's not a matter of... So we just need to ignore whatever's in the middle. And so how do we code this solution? Well, it's not... I can't think of an obvious way to make this like completely array-oriented. So I'm going to use a bit of, I think, recursion. Yeah, I'll use a bit of recursion with an auxiliary function. So what the auxiliary function is going to do is simulate this thing of pointer-like stuff where we want to... So let's find the targets. This is a function that is trying to find the target and it's going to sum the endpoints. So it's going to take the first element of the argument and add it to the last element of the argument, right? And then if the sum matches the target, which is going to be on the left, we return these two elements. So we're going to return the first and the last of the argument. Otherwise, if the sum is greater than the target, we need to get rid of large elements, and therefore we go down, we recurse with the del character, we recurse, but we drop the last element of the vector because it's too large. Otherwise, if the sum is smaller than the target, we recurse, but instead we drop the first element. So, for example, if we try to find the target 9, what was it? The target 9, and then if we give this input, we get the 7 and the 2. So this is our auxiliary function, and then what our solution does is, assuming the target is on the left, it's going to take, so the numbers come from taking the target, passing it to the find target, and passing it the original vector, but we need to sort it first, because this only works if the argument is sorted. So this is sorting the vector, and then we find the target, and then what we need to return is the indices of where the numbers were. So what we do is, let's see, if we take the vector, we check which elements of the vector are in the two numbers, and then we return a where. Now, does this work? Not necessarily, because I don't think there are no guarantees about the uniqueness. You can return the answer in any order. So we get the numbers here. The 3, the 2, and the 4. We would get a 2, 4. That would work, but then we would get a 3, 3. And when we get a 3, 3, what happens? Let's see. I'm not sure this is correct. So let's see. Let's make this the target 6, the solution 3, 3, 0, 1. So this is fine. But now what if? So this same vector, but I don't know, with an extra 7 in here. Now target 9, solution vector, right, 1, 2, 3. So this is not supposed to happen, because there's multiple numbers here, and it finds the 7, finds it twice in here. So our initial step is fine. It's just that we can't get, we can't retrieve the indices like this. Well, we don't need to be too smart about it. So the index of the first number, that's going to be the first of the where of the argument equals to the first of the numbers. So that's the index of the first. And now the second is going to be the index of the second is going to be the peak of the where of omega equals the second number, which is also the last one. But now, when we do the where, first we need to get rid of this index so that it's not repeated. So we can do something like this. Then we just return the two, index of the first and index of the second. This works, although it's a little bit ugly. 3, 3. Yep. So of course we can simplify this to be the index of the first together with that one. Right, so there you have it. To be honest, I'm not very pleased with the way we finished this, so I challenge you to improve this piece right here. But let's call it the core of the problem was in implementing something like this auxiliary function ft. So yeah, this is how you can solve problem 1 in less than O of n squared, and specifically in n log n. And I'll see you around. Bye.